Okay, thank you to the organizers for inviting me again to this workshop in the city. So I'm going to talk this time about how do we go from scratch, like purely defining a topological phase, to actually prediction of that phase in a material and the experimental realization and topological signatures. So with that, we usually follow 3 steps. First is the classification of topological phases in insulators and metals or semimetals. Then we try to realize these robust topological phases in materials, predicting these phases by a different elimination technique. And then we try to actually prove them, collaborating with experimentalists and detect these experimental signatures. First, also working with more methodological people, and then with the experimentalists that realize these, that measure these topological features in materials. Okay, so following these 3 steps, this is going to be the outline of my talk. Introduction and motivation to the topological semi-metallic phases. Then the first prediction, realization, and experimental measure of high-order nodal points in paramagnetic materials. In the following, I will give you the theory behind the identification of magnetic crossings, high-order crossing in magnetic materials, and the attempt of the experimental realization of the materials, comparing what the experimental can tell us, how can we help experimentalists with DFT and prediction of phases, and usually, and some examples of the results of these collaborations. All right, so the motivation to look deep into semi-metallic phases of high-order topological material comes from this paper by Fernando Adolfo that they got published in 2017, and it's about the circular photogalvanic effect that Adolfo introduced already. I'm sure Fernando will talk about it again. So I'm just going to give a superficial explanation of how it works from a materials perspective. So the CPK is the part of the photocurrent that switches depending on the circularization of the incident light. And what Fernando and Adolfo found is that when the material holds a chiral, when the material is described by a chiral space group, which is a space group that lacks mirror or inversion, the response of the injection is quantized in terms of the charge, age, and the turn number. So if we have a material in one of these space groups, we're going to have between high symmetry points 2 vials. We can have 2 vials crossing that are going to be at the different energies, and they're going to have a quantized response function. This is going to be for the turn number equals 1, and this would be for the turn number minus 1. So I started talking to them, and the idea was to actually find a material that could hold these vial crossings. And the group of Hassan predicted extrusion site as such realization of the phase. It has these 2 vials crossing in a very clean structure between gamma and X, and it could be ideal for this type of experiments. But they tried to grow it, and apparently it's impossible to reproduce the only paper that claims to have grown this phase. So we started looking for more materials with these crossings. However, we did not really succeed finding these crossings between high symmetry points. So the hope came back again when high-order nodal semimetals were predicted at high symmetry points. So we can find high-order nodal semimetals in materials by looking at the n-fold energy degeneracy at the high symmetry points. And this is given by the n-dimensional irreps of the little group. And this is easier to find because if it happens on a high symmetry point, it's always going to be there. So in this work with Jen, Berry, Andre, and Sichon, we predicted that actually we could find these high-order nodal crossings also in chiral space groups, such as 199 and 240, where a threefold degeneracy was found at the high symmetry point. And because it lacked mirror and inversion, this threefold crossing hold a large turn number. And the same happened with a sixfold degeneracy in this space group here. We also proved that the Ks Hamiltonian of the little group at these high symmetry points can be mapped to a spin-1 matrix, and also that one of the experimental signatures could be a double Fermi act between two high symmetry points. Okay, so inspired by this paper, where they presented a very ultra-simplistic type model of the generalization of the CPG for high-order nodal semimetals, since Barry and I worked together in the first paper that predicted high-order nodal crossings, and I was already talking about this with Fernando and Adolfo. We got together to work in the generalization of the CPG. So Fernando, Adolfo, Barry, Takahiro, and Felix, we got together without Joel, by the way, and we generalized the CPG for high-order nodal crossings. So considering a K.P. Hamiltonian from our original paper, we, mainly they simulate the CPG for a band structure such as this one. So the K.P. model depends on one parameter that actually describes the shape of the bands. Because if we have two linear dispersion, it's easy, but when we have a higher nodal crossings, the dispersion of the bands is important. So the response is going to be different. For example, if this band is completely flat or not. So what they prove is that for some values of the parameter, we can actually see the quantization in these higher nodal crossings. And in the same paper, we did, let's say, more deep classification of the nodal crossings in the chiral space group. And we provide this table where actually here are listed all the Swift groups that can hold non-diagonal element, matrix element in the CPG, and here the ones that one should find or measure. Okay. In the same paper, we also presented more materials where the threefold cruising is close to the Fermi level, because so far no one has measured a material with a threefold cruising, and also another material with a clean band structure with a fourfold also close to the Fermi level. All right, so this was the motivation and the semimetal classification, and now we go to the experimental realization. So this was basically motivated by Niels, and I'm sure he will talk more about this material and what are the physical amazing properties behind, but I'm going to give you some insight on the first material that actually was predicted in our original work and was proved experimentally. So it was aluminum platinum. It was grown in the group of Claudia Felser, and this is the band structure. So at gamma point, we have a spin 3 halves in the fourfold cruising, and at the R point, we have a spin 1 in the sixfold cruising. So Niels got this material, and he cleaved it, and he did RPS data. He got RPS data. So it's a very, it's a very, very nice and clean RPS data that actually proves that sixfold fermions exist there. And it was the first time a sixfold fermion was measured. It's in an amazing agreement with the DFT calculation, even the energies. So here we have a sixfold cruising that was predicted by DFT calculations. And then if we look at the surface states, here we have the DFT calculations and here the experimental data. We can see the double Fermi arcs going from gamma to R that is reproduced here in the experimental data. So we were actually very happy with this experiment. And furthermore, the same year, Lou, Orenstein, and Claudia measured for the first time the photocurrent response of rhodium silicide, another material that holds a sixfold fermion. And they showed that there was a plateau that was independent of the frequency, and it's believed that this is due to the larger number because it's very close to 4. And this would be the first experimental measurement of the circular photogalvanic effect that Fernando predicted some years ago. Okay, so, however, we always find the sixfold below the Fermi level. And we wanted to actually put it at the Fermi level because like this, some other transport experiment can be done and reveal more topological signatures. So we thought that one way of lifting up the 6-fold to the Fermi level was by designing an alloy. The aluminum platinum belongs to a family that has a lot of different compounds. So one is, for example, magnesium platinum that has the 6-fold over the Fermi level. So we thought about designing an alloy that could lift the 6 point right here. And this was the stoichiometric formula that could actually do it. We talked with Claudia, but it was not actually possible to grow this material. So in the end, the only way to actually go for higher order nodal crossings at the Fermi level is by start looking at magnetic compounds. So why is so difficult to find higher order nodal crossings in materials? And this is an explanation that actually Leslie gives in her talks, but it's very intuitive and easy to understand. So when we add non-symmetric symmetry operations that are the ones stabilizing these higher order nodal crossings, what we are doing is enhancing the real space unit cell. And when we enhance the real space unit cell, it contracts in reciprocal space. So what we find is a doubling of bands that actually are protected by symmetry. However, what usually happens is that these higher order nodal crossings have an odd number of electrons, and this is chemically very, very unstable. So what the material does is either you have the nodal crossings below the Fermi level, or it experiences a Peyer's distortion and breaks some symmetry, or it becomes a Mott insulator, or more naturally, when we have an odd number of electrons, it becomes magnetic. So the search of higher order nodal semimetals usually happens it has been done in paramagnetic materials because on one hand there is extensive databases to look for these materials with all the symmetries, but these databases lack the magnetic order. And the second one is because it's easier to analyze the symmetries of 200 space groups. When we deal with magnetic materials, we have to add a combination of time reversal and other symmetry operations, and we go up to 1600 materials. But magnetic semimetals are very interesting because the same material holds different phases, and we can tune these phases by changing the temperature or applying a magnetic field. So, by Jen, we start this project by trying to look at magnetic semimetals. In the same way, we look for non-magnetic metals by looking at the dimension of the co-representation at the high symmetry form. The way we did it is the following. So in a gray space group, we can define it as the sum of two cosets. One is H that holds all the symmetry all the spatial symmetry, and then we can apply the reversal symmetry to H. So then reversal symmetry is an operation that does not change nuclear variables, but change the sign of all atomic magnetic moments. In this way, our PNMA space group would be PNMA1 prime, which is the part that lacks time reversal symmetry, plus time reversal symmetry applied to the full space. When we deal with magnetic groups, time reversal symmetry is not there or is combined with other symmetries. So it can be combined with translation or with mirrors, and this sums up the magnetic space group, the 200 magnetic space group, the 1600 magnetic group. So to look for the dimension of co-representation in magnetic groups, we're gonna use the classification that has been done already in magnetic group, which is divided in type 1, type 2, type 3, and type 4, depending on how we combine the reversal symmetry with other symmetry operations. So type 1 lacks the reversal symmetry completely, and to find the dimension of the co-representations, we just need to look to the tables that we have and get the dimension with time reversal symmetry. Type 2 are the 230 space group that we already know. Type 3 has a time reversal symmetry combined with integer translation, and type 4 has time reversal symmetry combined with fractional translation. And this is the bubble that we use to look for material. So that one, it's pretty much straightforward to find. Type 2 are the non-magnetic ones. For type 3, we see that type 3 and 8 share the same unit cell, so we can find the high dimensional E-reps of G prime in G. And for type, for type 4, it's more tricky technically. So an algorithm is given in this book that actually, following it, we can find the high order nodal crossings in magnetic materials. And since we are only looking at high symmetry points, here is like a recipe of the space group that can hold a 3-fold, 6-fold, and 8-fold nodal crossings, as in the paramagnetic case and the Bikov positions. Of course, this is for, in principle, it's for non-interacting phases, but I will discuss this in a second. All right. So, following this recipe, we look for some material realization. And one very interesting one we found is magnesium P iridium silicon that was predicted by Ericsson and his collaborators in Uppsala. So this compound is a type 1 without any magnetization. It holds a 6-fold crossing at the R symmetry point. When we let it magnetize in an antiferromagnetic phase, as here, what we find is that the manganese forms a triangular antiferromagnetic networks at the end of the bound to the silicon, and all of them form an antiferromagnetic structure. We calculated the band structure for U, Havar U equals 3, and we found a 3-fold crossing at the Fermi level. So this U equals 3 actually reproduced the magnetic moment that was measured. But is this actually true? I mean, is a 3-fold here? This is something we don't know, because when we have a chiral space group magnetized in antiferromagnetic way, usually the strength that provides DFT is not enough. So we will only find out whether there is a 3-fold at this point or not with experimental realization of the compound. And we made up this magnetic structure just to show you the level of complexity one needs to reach to find these high order nodal crossing in magnetic materials. So it's an antiferromagnetic with this very weird way of arranging the spins, but after the band structure calculation, for in this case U equals 0, because anyway this phase has not been reported, we find an 8-fold crossings at the A point that actually realize the Dirac rarity transfer from Young.
There's a prediction.
Okay.
Height.
So now we go to experimental realization. So experimental realization, I've done collaborations 3 times, and this was the first time collaboration with Leslie of Princeton. So we wanted to find a magnetic 3-fold, because finding a 3-fold in paramagnetic phases was really hard and was also actually never close to the Fermi level. And we decided to go for a magnetic phase in a 6-fold space group that would split the bands. So we look at the database and we found this family, and we pick up the first one because they reported a magnetic moment from iron. This is the band structure. We have these 2 6-folds for the paramagnetic phase close to the Fermi level, and when we let the iron magnetize, the 6-dimensional E rep is split into 3-dimensional E rep plus 1, as we can see here. We also calculated the band structure of the phase of another phase, where we also in another chiral space group, where the iron splits in 2-dimensional E-reps along their point, and the calculation reproduced the magnetic moment and the Curie temperature that actually was reported, and this was really cool. We even calculated the experimental signatures of the surface, and we found this topological surface state. However, when they try to draw this material, it happens that the experimental paper that reported the space group was wrong. So the black line here is the measurement pattern. The red one here is the simulated intensity for iron in the space group we wanted, and the blue one is what they measured. So these little peaks that and the blue one is the simulation for another space group. So the little peaks here that we don't find in the blue line are actually like very important, and what we really measure, what the phase that actually holds the compound is not the chiral space group, it's a non-symmorphic space group 2, but with a glide and inversion. Because actually, the original stoichiometric formula we were looking for, it was a deformation of actinic space group. And what is really happening is that what we have is originally pyrite that actually are realized in this space group contaminated by iron. So they did the hysteresis cycle, and they calculated the Curie temperature, and it's ferromagnetic. So we thought, okay, well, since we have this material, let's look at this material. In the paramagnetic phase, the band structure looks interesting. It's a semimetal, but when we let it magnetize and we dope it with iron, even going beyond DFT by more sophisticated ways of calculating block spectral functions based on green functions, only with a little bit of iron, the bands hybridize so much that it's impossible to see anything. And if we add even more, it becomes something really blurry. So this was the end of this story. Maybe Arcus measurement of the alloy could give some extra signal, but there's not much more we can do. The second experimental realization was in a non-symmorphic topological material of the family of the square net compounds that Leslie likes very much. And we have cerium, and cerium is a rare earth, and it has 8 electrons, and this can be something very complicated with DFT. So the first thing we did was to calculate the band structure with DFT, different pseudo-potentials, and different ways of adding the F electron to the material, and compare it with ARPES data. And we see that when we add the F electrons to the core of the pseudo-potential, we remove them from the valence band, we find a very nice agreement between experiments and ARPES. This is because it's a Curie-based magnetic material. Once we can rely on the DFT setup, then we look at the different magnetic phases that this material can hold. So by adding an external magnetic field of this number of the 2 Tesla, 0.25 Tesla, and above the Curie temperature, we can find these phases that are ferromagnetic phases. Below CK and no field, we find an antiferromagnetic phase, and this ferromagnetic phase is a type for magnetic material. So EFT calculation at the same high symmetry point, but for different magnetic phases, give, of course, a different band structure. So the paramagnetic one, for example, at X has a 4-fold degeneracy. If we add the magnetic field in the direction 111, it splits. In the 001, it also splits. Then we have these cruisings, and for the antiferromagnetic phase, we recover the false Flatiron because time reverse and symmetry is combined with translation, and it's preserved in this way. And if we go way below the Fermi level, we find that, but very below, like almost minus 5 eV, that actually the 8-fold magnetic crossing can be realized at the 8 point. Okay, and the last one is a pyrite, in a pure pyrite in the TA minus 3 space group is a non-symmetric to like space groups, and we look at the pyrites first because we had this space group reported in our original paper, and also because pyrites by itself are very interesting family of materials. They are very good semiconductors. They also hold superconductivity and have metallicity. This is the crystal structure of our compound. This is the unit cell from the XY plane. So the cobalt atoms are at the corners, and the sulfide atoms are like attached to the cobalts by a non-local parameter x. So this is what is reproduced for z equals 0 and z equals 1.5. Okay, so now we let it magnetize and ferromagnetic waves. Actually, this compound has a what is called soft magnetism. The ferromagnetic phase is not, it's unclear in what direction it's pointed, and it's very easy to manipulate under a magnetic field. So we choose the 001 magnetization. So now, what do we do with the calculations? What is the value of Q? Why pseudo potential we should use, LDA, GTA? So thanks to Niels that we have in the team, he did ARPS measurements, because the first calculation we did was with Q equals 3 and GTA, which is what the transition metals usually, the parameters for 3D transition metals. And it happens that the conundrum of this material is this bucket that we find at R that we actually cannot see with U equals 3 and GTA. And we did calculations with different values of U for GTA, and it was absolutely impossible to get this bucket. So we then consider U equals 0 and LDA, and the bucket at R showed. So what does this mean? I mean, what type of magnetism is this one? So on one hand, it works for U equals 0 and LDA. And then we can see that the energies are not equivalent. Like the band structure is renormalized, right? I mean, they are like squeezed. And it happens when we have itinerant magnetism. So DFT cannot reproduce this magnetism. We need a dynamical mean field approach to actually reproduce it. But once we have identified this, we can use band theory to actually reveal the most interesting electronic properties of the material. And there are several interesting features. At endpoint, we have a magnetic fourfold Dirac crossing, and we also, or Niels also, can reproduce this feature here, renormalize, as I said. And we also did calculations of the energy cuts for U equals 0 and LDA, and we see a nice agreement for the sulfide termination of the measured ARPS measurements and the DFT calculation. And well, the paper is still in preparation, and more interesting electronic features will come up. So,
excuse me, these red lines, they are from your arc? Or?
No. It's the intensity, they are not from the arc.
Okay, just normal
No.
surface state.
No. Yeah. I mean, so far we don't know. But, it doesn't.
Okay.
It's just the intensity of the calculation. So the topological magnetic semimetals open the gate for many different experimental realizations. By means of group theory, we can predict high order crossings at high symmetry points. And while I have introduced several experimental collaborations with magnetic materials, and we see that actually DFT works quite well, but we need to be careful with, we need to be very careful and work very closely to actually predict the properties in a fair way. Thank you.
Okay, we have 6 minutes for questions. So,
the alloy materials that you were talking about. So you said in the end, what was that, like aluminum, platinum stuff? Like in the end, you said maybe they couldn't grow it or it was unstable. But do you think, we're talking about phases which rely on crystal symmetry. So do you think that alloys would, if they preserve the crystal symmetry on average, then they would still exhibit kind of phenomena like this, or?
Yeah, I mean, if you drop it like massively, maybe it's more tricky, but if you dope it, I mean, like, with doping, let's say, and it preserves the symmetry in average, I believe the green function has the symmetry of the crystal. But this is for grid function.
Yeah.
So we don't have it.
There's no band structure, because yeah, that's kind of interesting, I think.
So how does the 4, 6, and 8 fold differ in magnetic groups from non-magnetic groups? What's the what is the fundamental physical difference? Do we know? I mean, I know it's not very well known for even what's the fundamental physical difference for 8-fold even in non-magnetic groups, but
I mean, I only look at well, I start looking at the span structure symmetry properties of the chiral space group that like mirror and inversion, and I was only interested in the transition to another chiral space. So I believe there is a conservation of the turn number. So I would guess that it should be somehow the same nominal charge as in the original one. For the rest, I think it's a very complicated.
I have two questions. First one is in terms of the chiral while semimetal. So actually, what's the story about tellurium? The single atom tellurium. So why is that difficult to realize the chiral while semimetal phase? The doping or what?
I think the problem, I mean, I think maybe Fito and Fernando knows more, but I think the problem with tellurium is that it's very hard to dope. I mean, the doping is difficult with every material, so tellurium actually is hard to dope.
Second question is that so in the morning, Barry said that in chiral system, like any twofold is wild, right? That's what you say in the morning. So then, in the space group 198, at the R point, so it should be 8, right? So without spinal carbon is 4, and we consider
And
it's
our
8.
point is in what? In which one?
198.
It's 6 at our point.
So where is the other twofold?
At gamma.
No, at R. Gamma is 4 plus 2, right?
You have a 6-foot here, and here you have the 2.
But is that wild?
No, you have an error of 2. But I don't think this has a. I mean, this is not a vibe.
It looks like it's doubly degenerate along RX, so it's not linear in all directions.
Not a point across.
So it's like a nodal line that splits in some directions.
So then at
That's a
gamma,
good question.
so then at gamma it's a wild. No, 4 plus 2. That's 2.
This is the 4-fold, yes.
Yeah. So but there is another twofold somewhere, right?
Yeah.
So that's wild.
This is a vibe.
Okay. I see.
It's a while from the other paper. Well, it's a Cronmer's while.
Any other questions? Maybe I'll ask another one. So then in the magnetic, I didn't catch what does the G prime H mean in the magnetic group? Be like a type 1, type 2, type 4. What are these mean? G prime H.
This is the unitary part of. So this is it's a bit more elaborate. So this is the unitary part of the symmetry operations that are actually reduced simply by adding time reversal symmetry. And here we try to find the overlapping between starting from the same type 1 and adding time reversal symmetry operations in combination with other symmetries to find a common overlapping where we can easily look at the dimensions of the curve representation. You want to answer?
Yeah. So one thing is that, let's see, the notation that we're using here is that these type 1 groups have, they don't have time reversal. Okay, so all the symmetries then are are unitary symmetry. They're just crystal symmetries. And then you can consider adding time reversal, and now you have all your unitary symmetries, and you also have a set of anti-unitary symmetries, which is just time reversal, a product of time reversal, and any of your original symmetries. In these magnetic groups, you can have weird combinations where you don't have a symmetry, but you have the product of that symmetry and time reversal. And so that's kind of what these different types are. Like you can see like in this lower picture that Maya has, it's like when you rotate the hexagon, so you don't have a six-fold symmetry, but you would have like a six-fold and a spin flip. So you have these combinations, and so that's when you have to kind of distinguish like what is the subset of unitary symmetries, and that's different than the subset of anti-unitary symmetries, and together they form a group still. Yeah.
Any other questions? If not, then I think Maia.